So bond breaking is always endothermic. And that means that bond forming is exothermic.
So you don't need to put energy into bonding?
Yeah, you don't. It just happens automatically. Let's think about the creation of an ionic bond. Okay? Let us start with a positive ion, a cation, and an anion. And let's say that they come together. Okay? Where are they at a higher potential energy state and where are they at a lower potential energy state? Where are they more stable? They are more stable when they are together. Okay, so this is more stable. In other words, lower potential energy. This is less stable. This is higher potential energy. So if we have gone from high potential energy to low potential energy, have we taken energy in or have we had energy go out? We start, here's our start, here's our finish, and this process is the bonding process. At the start, the potential energy is high. Okay, that's when they're far apart. At the end, the potential energy is low. So bonding is exothermic. I always find that one's a little harder to think about. So if you just want to remember, it requires me to put in energy to break the chopstick. Breaking bonds is endothermic, therefore forming bonds must be the opposite. So it must be exothermic. Okay, so if you can remember one of them, you know both of them. All right. So in a reaction, if it takes more energy to break the reactant bonds than to form the product bonds, this is the endothermic process. And the forming of bonds is the exothermic process. And if endo requires more energy, then the whole overall process will be endothermic. It's like if you had to put in 10 kilojoules, but you got out 8 kilojoules, you still had to put in a net of 2. Okay? So what that ends up looking like is, in this particular case, here is how much energy it takes to break the bonds. So breaking our bonds. We start out here. We go up to our broken bonds. Everything's been broken apart. We are now at a higher potential energy. And then, as the new bonds form, that is exothermic. So we have the endothermic process and we have the exothermic process. And in this particular case, the endothermic process required less energy than the exothermic process gave out. And so overall, delta H is negative because the exo was larger than the endo, which was smaller. You don't have to think about this too much. This becomes a bit of a little brain. It makes my brain hurt sometimes when I think about it. Okay? What you need to realize is this is actually how reactions happen. Old bonds break, new bonds form. So rather than having the graphs that look like we had yesterday where it just goes doom, 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 instead, we're going to have a graph that goes up first and then down. But we actually don't draw it all squared off like that. What we have is we have our reactants, and then we have a nice smooth hill, and then we have our products. That's supposed to be a nice smooth hill. I just can't draw. Okay? And that's what our potential energy diagrams are going to look like from now on. And this amount of energy here, from the reactants to the peak, that is our activation energy. The energy required to break those bonds, that is our activation energy. Okay, so if we go across like this, and I'm tired of writing activation energy, so I'm going to show you the abbreviation for it. It is E with a little capital A down at the bottom. That is the energy needed for a collision, minimum energy needed for a collision to be successful. Because if you don't break the bonds, you can't have new bonds forming. You have to break the old bonds first. Okay? What's the other word for successful? Effective. Is good? Yeah? Okay, cool. Okay, why are you not moving now, Mr. Screen? Come on. Behave. There we go. Okay, so our potential energy diagrams will now look like this. This shows the nice smooth hills. So when we have an exothermic reaction, that was supposed to be a highlighter. When we have an exothermic reaction, our delta H is negative, and you'll notice that the bonds being made gives off more energy than the bonds being broken absorbs. All right? Endothermic is the opposite, so it takes more energy to break those bonds. And in this case, our activation energy, it's still how much we start from the reactants. How much does it take to break all those bonds? That is our activation energy. You can use a little a or a big A, it actually doesn't matter. Here's just another picture. I don't know why. I had another half page to fill on this sheet, and I thought, hey, this one looks kind of nice. Okay. The energy required to break the bonds is known as the activation energy. Minimum amount of energy needed for a collision to be successful. We said that already. Moving on to 1.3D. See, this is how I do it. James? This is how I do it. Moving on. See? All right. All reactant molecules, we are now on page 63. All reactant molecules have some specific amount of potential energy in them. As molecules approach one another, there is always a repulsion between their electron clouds. You remember the outside of atoms and molecules are made of electrons. So, electron A looks at electron B. These electrons see these electrons, and what do they do to one another? They repel. Okay, so there is a repulsive force. And if I have two things that are moving quite quickly, zoom, what happens to them if they start being repelled? Zoom. They're going to slow down. And what will happen to their potential energy as they get closer, as I start trying to push these things that are repelling each other together? What happens to their potential energy? Their potential energy goes up. So that's another way to think about why the potential energy goes up as the reactant particles begin to collide, is that their electron clouds are repelling one another. So, because if you think about, do I have two magnets that are going to repel each other? Don't know that I do. I found one the other day, but mostly they just attract one another, and that's kind of annoying. Let's see. No, those just attract one another. Nope. Okay, that's a futile sort of a thing there. But you know what it's like. You've pushed magnets together, have you? Everyone has? Okay, if you haven't, come and see me and I'll see if I can find some magnets and we can try pushing them together. Literally, it's like, and they're like, and it's really hard, okay? It's like pushing a spring together or something like that. So as a result of the repulsion, the kinetic energy decreases and their potential energy increases. And that is that activation energy peak on the potential energy diagram. As we said before, kinetic energy is converting into potential energy because the kinetic energy is decreasing, potential energy is increasing. Now, if the particles are approaching with the correct alignment, orientation, what's another word for that? Geometry. And if the particles have sufficient energy to overcome the repulsive forces and break the bonds of the reactants, then an activated complex will be formed. What the heck is an activated complex? This is a new word. It also starts with active. So you've learned activation energy. Activated complex starts the same way, but don't confuse it. It's a different word. Okay? And in fact, if we went back to, whoops, come along. If we go back here, this nonsense right here, that would be our activated complex. We don't really know what it looks like, okay? Bonds have been broken, atoms are sort of all over the place. It's a big messy mess, yes? All that we know is that it's at a really high potential energy. Do things at high potential energy tend to stay that way for long? No. So it's actually a really short-lived experience. Like that little particle, whatever the heck it is very, very short-lived, and it will very quickly turn into product molecules. Okay? So let us define activated complex. So our activated complex is short-lived. It has a high potential energy. It is unstable. Those all kind of mean the same thing, but we'll give them all. And what is it? It is an arrangement of atoms.
It breaks apart and then make it back together.
Yeah, so it's an arrangement of atoms that exists when molecules successfully collide. So we don't know what it looks like. We just know that the bonds have broken apart. It looks like something, it never lasts long enough for us to isolate it and study it, which is why we don't know what it looks like. Okay. It is also known as the transition state, but I would not worry about this term. Don't worry about this word. Don't worry about this word. I've just put it there because I think some of my things reference it from time to time, but you're not responsible for, calling it that. Okay?
And you in the bond break apart and go back.
Can the bonds break? Yes, they can. You can actually form an activated complex and have it go back to reactants. Yeah. So sometimes you'll have a successful collision and it'll go back to reactants. Sometimes you'll have a successful collision and it'll go forwards to the products. Okay, so this word, you must memorize this definition. And actually, we are kind of getting into definition territory. So what I'm going to do is I'm going to get you guys all of the words for Unit 1. Okay, 1, 2, 3, 4, 5. Take one, pass it along. 1, 2, 3. No.
At least you don't make us do both have proof.
1, 2, 3, 4, 5. 2, 3, 4, 5. This is true. Oh, yes, that's So actually, if you look at the very first definition there, it is the definition of an activated complex, and it shows you a picture of the activated complex, which is basically just all the reactant molecules smushed together in some way that we don't know how. Okay? So this will come in handy for you as you go to study for your test. You can also go through it when you're studying for a quiz, and you can be like, on my next quiz, maybe not your next one, not the one on Friday, but like the next one, you'll need to know what an activated complex is, so you can study it from here if you want to. Okay? I don't have these for every unit. This is just a vocab heavy unit. All right, here's that picture again. It is so unstable. It is so short-lived. We can't actually isolate it or study it. And so when we write a reaction, when we write the equation, it doesn't show up, right? If I was to write the equation for hydrogen and oxygen reacting to form water, I would normally just write 2H2 plus O2 gives 2H2O. Do you see an activated complex anywhere? No. If you had to put it somewhere, it would occur in the arrow. But we don't. Like, it's just, that's where it would be if you could see it, which you can't. Okay? And we will often put a star beside it. The star means, I'm super reactive and high potential. Okay? It means I'm the activated complex. And how do you figure out this formula? How did I figure out to write H4O2? I just smash everything together. I say I have 2 times 2 is 4 hydrogens, and I've got 2 oxygens. And I just smush them all together.
Please straighten it out. No, straight out.
What's up? You're good?
Yeah.
Okay. Okay, so they just smush together. What are the chances of you having to write an activated complex's formula? Slim to none, I think. Okay? But you should recognize what it is. Sometimes we just say, look, there is our activated complex. And we can show the entire potential energy diagram with the little molecules. We have our reactants down here. Here's our reactants, and the reactants molecules are approaching one another. And the bonds break. And then, so this is number 1, we have our reactants, just reactants. Number 2, they approach each other and the bonds break. Number 3, we have our activated complex. And number 4, new bonds form. And the product particles move away from one another. Product molecules move away from each other. And then finally, you just have product. I need to fix this. Because I don't want to have this little arrowhead up here. I want that to just be straight down. There we go. Because, and I don't want this thing here. I don't want that there. I just want this to go straight down. From the reactants to the peak is the activation energy. From the reactants to the products is our delta H. So now we have a couple of energy quantities we can label on a potential energy diagram. We can label delta H, we can label EA, activation energy. Is this an endothermic or an exothermic reaction? This is exo. Remember? It's going down, and you go down the stairs when you exit the building. Is delta H positive or negative? It's negative. Where would our kilojoules go?
Kilojoules, it goes on to the power.
Kilojoules go on the right. Excellent. Good.
If it's the endo, to the kilojoules in the reactant side,
Yes, if it's endo, kilojoules go on the reactant side. Yeah.
or we could just put on the side, right? Like kilojoules equal to no, like
You
delta
could
H.
put delta H is equal to whatever kilojoules, positive or negative. Okay? That's alternate ways of doing it. Okay, so this kind of just breaks it down again. Nothing new here. I guess we should say, in this part of the graph, when we're going up, kinetic energy is converted to potential energy. Therefore, the particles do what? Do they speed up or do they slow down?
Slow down.
Slow down. As we go down, the product molecules move apart and potential energy is converted to kinetic energy, and therefore the particles speed up. How are we feeling about this graph? Are we feeling comfortable-ish? Ish? Yeah, okay. So this is our barrier that you have to get over. All right, you can imagine it's just like that hill that all the people in Burnaby have to go walk up the hill. Did I talk about this in this class with all the people in Burnaby going for a walk over the hill? Some of them are going to make it over the hill. Some of them are not going to make it over the hill, right? And it's just going to depend on how big the hill is and how energetic the people are who are going to try to get over the hill. All right? Okay, activation energy, we've already defined that. It's here, memorize this definition. Minimum energy with which particles must collide for a collision to be successful, or the minimum energy reacting molecules must have in order to form the activated complex. And this is what you were talking about earlier. Sometimes the reactants can go up the hill and then they just, oh, hang on, no, that's not what I'm talking about. This is where they don't have enough kinetic energy to go all the way up the hill. They just kind of like get close to each other and then they're like, yay, and they bounce off of each other without actually touching.
Geometry, but not enough energy.
Yeah, not enough energy. Yeah, okay. So, labeling, you should be able to label delta H. You should be able to label EA. You should know that your y-axis is potential energy, and you should know that x-axis, you can call it reaction progress, you can call it progress of reaction. You can say reaction proceeds.
Can't just write reaction.
You can say, what's the other one?
Okay.
I can't remember. Doesn't matter. Okay. Let's see if we got them here. Eric is here. Yes. And so is Isabella. Thank you. Oh, here, take the paper clip. There you go. Okay. Isabella. And Eric. All right. Now there's one more. So we have 1, 2 things. There's a third thing and it's confusing because it sounds just like the other thing. Okay? The energy of the activated complex
The whole thing.
is different than the activation energy. It's just like the reactants are here, yes? Our reactants are here. This is our energy of the reactants. We never label it, but that's how you could label it, yeah? that's the potential energy of the reactants. Well, what is the energy of the activated complex? It is literally the energy of the activated complex, and you can label it with an arrow here, or if you want to, you can go over here and say, let's just say that this is 2 kilojoules. Let's say that this number up here is, what shall we say, 14? 14 kilojoules. And then let's say that this is 23 kilojoules? Sure. So if those were our numbers, then what is delta H?
Negative.
Negative how much?
Like, no, 12 kilojoules.
Negative 12 kilojoules. Okay. What is the activation energy?
9 or negative 9.
Is it negative 9 or positive 9? Positive 9. So our activation energy is positive 9 kilojoules from the reactants up to the activation energy. What is the energy of the activated complex? Sorry, this is a 3. Here, I'll just put a little arrow because it's hard to read when it's over top of that. This right here is 23 kilojoules. What's the energy of the activated complex? 23.
What? The whole thing.
Yeah.
But no, no, but it starts from 2, no.
No. What's the energy of the reactants?
14.
Okay.
No,
So that's 14 kilojoules. What is the energy of the products? 2 kilojoules. So the potential energy of the reactants is 14 kilojoules because that's where it is. The energy of the products is 2 kilojoules because that's where it is. What is the energy of the activated complex? 23 kilojoules because that's how much energy it has. Why is this confusing? I don't get it. That's how much energy it has. Yeah? It just is how much potential energy there is in the activated complex. But it's not from 23 to 2, it's from 23 to 0. This down here is 0. Like delta H would be here. Yeah, so that's 12. Yeah. Yeah. You don't get asked about the active energy of the activated complex often, but it does come up. You can take your chances. You can be like, I hope I never get a question like that. Sometimes there are things like that. I know when we got into the acid rain section. Okay, just so you guys know, literally the Chemistry 12 course has not changed since I was taking it back in 1989. Has not changed. Same course, same exams. I could give you guys my final exam that I wrote for 50% of my grade. I could give you my actual final exam that I wrote because I have a copy of it. Okay, I've got all the exams going back to 1985.
Wait, is our final exam also worth 50% of our grade?
I don't think we're going to have a final exam.
Yay.
Yeah.
Okay, Yeah, but, so yeah, sometimes I played games, like I would be like, I don't really want to memorize all the equations to do with how acid rain formed because I didn't think it was likely to come up. So I didn't bother. Fortunately, it didn't come up, but I could have, that could have hit me for a couple of marks here or there. So, energy of the activated complex, could it come up? Yes. Will I probably put it on a quiz? Because I like to put things on quizzes that tend to trip people up. Not because I'm evil, but so that you will remember them when it comes to the test. Okay? Just so we're clear, I don't put things on quizzes that are tricky to be evil. I do it so that you will remember them. And so the energy of the activated complex is one of those things that because it sounds so much like activation energy, people get it confused with that. It's just a little bit of a weird concept, but you just start from zero and go all the way up to the top of the peak. So start at 0. Go to the top of the peak. I also wanted to mention on Friday, I've been saying Friday's quiz is about factors that affect rates, which it is, but it's also about collision theory because that's also part of section 1.2. So you should know the basic premise of collision theory. What is the basic premise of collision theory? We're just going to take a little break from this for a moment because I just thought of this now and I don't want to forget it. What is the basic premise of collision theory?
For the reaction to occur, particles must first collide. Must collide enough energy and the right proportion. Correct job. I got that. No, it's because it was in the homework. I didn't have it down that, so I just like wrote it basically just to memorize it. Yeah.
You're probably gonna have to check the,
That's okay. No worries. All good.
Can I leave at
Yes, of course. Thank you very much.
Collision that makes a reaction. Is that the correct way to say it?
I'll get out my cards again if I can find them. Oh, there's yellow. Okay. So have a chat with your neighbor about these. Feel like you could answer them if I call on you. Okay. Basic premise of collision theory. Beta. Very nice. And you projected well. I liked that. I could hear you all the way from the front. For a reaction to occur, particles must first collide.
Particles and molecules are the same.
Particles, molecules, whatever. I'll take either. I mean, particles just sort of expands it to ions and atoms as well, but I'll take molecules. What is an effective collision? Joshua? So the correct orientation. Excellent. So that's one of them. What does it mean to have an effective collision Kiona? No, that's okay. Isabella? No, that's okay. That's why we do this, right? Yeah? No, like, you're beside each other. Why would you? If one of you knew it, the other would know it. Not here. Noah?
Collisions that result in a reaction.
Yeah, an effective collision is a collision that results in a reaction. So for a collision to be effective, we need to have, number one, correct orientation. And we need something else. Matthew.
Enough energy that they.
Yeah, we need enough energy. Sufficient energy, but not enough sufficient energy. Okay, very good.
Yeah.
Okay, good, 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 good. Where were we at? We were at here. Okay. There. Why is the answer here? Get rid of answers. That way you could do them yourself. Anyway, you can feel free to read that. The answers are there, so it's not very exciting. Okay. I don't know. Do you guys really feel like you might need an equation to calculate delta H? If you do, it's the products minus the reactants, or you can just be like, I will just read it off the graph and not like have an official equation. To calculate the activation energy, it is the activated energy of the activated complex minus the energy of the reactants, or you can just read it off the graph. Ooh, what if we go backwards? Because you know what? In unit 2, we're going to have reactions that can proceed in the forwards direction, and then they can go backwards and proceed in the backwards direction, and actually both happen at the same time. They're called reversible reactions. Okay? Not all reactions are reversible, but we do need to know about them. Pardon me?
Some do.
Yeah. Okay. So if you have a forward reaction that looks like this, the reverse reaction is the mirror image. Okay, so the products become the reactants, and the reactants become the products. So what's going to happen is that now your reactants... Yeah. And the reactants become products. Now, you might not have a mirror with you when you're doing a question on a test. So, you just need to be able to read it backwards. So in the forward direction, our activation energy is from the reactants to the activated complex. If we wanted to label the activation energy for the reverse reaction, you can see the energy for the reverse reaction is here. It's from the level of the products up to the reactants. So we could actually draw that in here. We could say that this is the activation energy for the reverse reaction. So you just read the graph backwards. You start on the right and you move to the left. What would I do for delta H for the reverse reaction? I would start at the products and go to the reactants. So this would be delta H for the reverse reaction. They're the same value, they're just opposite signs. Okay? So if the forward reaction is exothermic, the reverse reaction must be endothermic. Delta H has the same value in the forward and reverse reactions if this sign is reversed. You are not going to be drawing mirror images. That seems ridiculous. Just read the graph from right to left rather than left to right if you're asked to do the reverse one. Okay. So this is where you could take an example and you could say, I'm going to read this. I want the reverse reaction. There's my activation energy. My forward reaction. That's our activation energy. Is good? Okay, that's it for that. Read it that way. Oh, look, one for you to read. Excellent. Try these.
Oh, we have to use a different color pen for this. Oh.
Do you?
Oh, no, I mean, like, it's just like activation energy for forward and activation energy for the reverse.
You can label them, but you can also just write down the values.
Oh.
But feel free to label them because that's also a good exercise.
Start on this page, go. Where are we? So you seriously end up with start at your reactants, yes. That's your activation. Start at 20s. Finish it under the activation. Yes.
They're really long worded thing. Really long.
And now you're calculating the reverse reaction. So now there's this negative thing. Oh my God.
Yeah.
Now. What's now?
This way, like that. This way. Like that. No. Oh, this way.
Yeah. Yeah. Yeah.
No, for C and D. C and D are the exact same.
I don't know. Okay, so
Good.
there's-
It's good. She's going the other thing.
Outside this, and that's where that extraction is coming from, technically you're not You're not creating energy, you're just bringing in energy. That's it. Yeah, yeah. Yeah, oh, the energy of the activating complex, zero. Oh, it's athletics.
B&B.
Yeah.
You got 8.7. I said you're smarter.
Yeah, I never said that. Oh my god.
You're deaf now too. Okay. Good energy. Oh wait, this band.
Yes.
So these for the both reverse and
Yeah.
it should be the same.
Yes.
Okay.
Yes. Yes. This one. It starts 5 inches low. This starts 1 inch high. You have to say, I start from my reactants and I go to mine.
What is, you get some
How do you
Sounds good. Yeah. Yes. Yeah, and then going backwards, and you start here. Okay. Yeah. 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 All the way to the top. So first, you start here. Right. Yeah, so you guys just put it on.
I know. But do you have to like memorize like do you have to like write down it's negative and then goes down it's negative?
What? For energy?
No, for like any of them, like it goes down. Like for example, the E and F, like maybe like for the still
Yeah.
Okay.
So the negative.
Yep, two different two. You
This looks good. Yeah. Then there's the same. Yeah. It's the
Yes. Oh, yeah.
Okay, we should get 80. Oh, that's not a pen. 80. Actually, do I have it on the next page? Oh, I do. Look at that. It's on the next page. We have 10 minutes left. Okay, let's do it. Effective catalyst on a potential energy diagram. Do you remember what a catalyst is?
It like it's up there but over the next question.
It speeds up the reaction by providing
But lowering
an alternate pathway.
make
Look,
it easier.
here's our alternate pathway with a, whoa, what happened there? That was crazy. Here's our alternate pathway with a lower hill. Yes? So it provides an alternate pathway with a lower activation energy. You need to memorize this definition.
Alternate track.
And what that means is that if the activation energy is lower, a larger percent of collisions will have sufficient energy. So Are we changing the nature of the reactants when we add a catalyst? No. So their potential energy stays the same. Products, their potential energy stays the same. The only thing that changes is the activation energy. Doesn't change delta H. Doesn't change the energy of the products and reactants, just the, oh, and I guess it changes the energy of the activated complex as well, but that's kind of implied. So you should be able to say, if somebody said to you, please draw the energy pathway for the catalyzed reaction, just make the peak lower than it was originally. Oh, this just says reactants and products stay the same. We already did that. So when drawing a potential energy diagram for a catalyzed reaction, draw the activation peak lower than the original peak and leave the potential energy of the products and reactants unchanged. We'll talk more about this later when we talk about reaction mechanisms. You may need to add more peaks to the diagrams, but that is okay. Now, we are running out of time, so let's figure out what you should do for homework.
Is that the math? Or the answer?
This is the same book as you have.
I thought that was like the math.
It's just so I can look at the pages. 44, 45. 44 to 47. Okay, how about, because your quiz is on Friday, and you want to do as much review as possible, how about you do pages 45 through 50? Yes, because that's related to Friday's quiz.
Take it, it's yours. Yes, enjoy. I kind of like, it's like break it, it's like a little bit springy. Yeah.
Got it.